All right, everybody, this is a video on trigonometric identities. Typically, when you get into trigonometry, you'll be given what are called trigonometric identities to basically memorize. And I find that slightly frustrating because in many cases, if you take a moment to actually dig into it, they actually make a bit of sense. And if you memorize it, you're going to forget it eventually. But if it actually makes sense to you, you can actually reconfigure it to get what you need in the future. So we're going to focus on one identity in particular because I think it's the easiest to figure out, and I think you'll use it quite often. This is going to be sine squared plus cosine squared equals 1. What's kind of funny about this is a lot of times they'll redistribute the numbers or the variables in this, the positions in this, I guess, to a different configuration and pretend it's a different identity, which I think is completely foolish because basically what they'll do is move sine over to the other side by just subtracting both sides by sine, and they'll call that a new identity. I'm going to explain why that's actually the same thing and how you can use that. But in order to do that, we're going to start with Pythagorean theorem. So a squared plus b squared equals c squared. This is arguably something that you probably memorize, and you'll probably never forget it. You may not really understand why it works or what it is, but you will remember it for many, many years to come. What you'll notice about this is we have a right triangle, and we have two sides, a and b. Here's a, here's b. And then we have this hypotenuse, which is c. If you square the two sides, it'll equate to the square of the hypotenuse. Well, if you look closely at this first formula, sine squared plus cosine squared equals 1, think of 1 as 1 squared. And now all of a sudden, you have these three values that are squared. Two of them yet add together to make the third. Well, we have two of them adding together to make a third, also imagine that squared number. So these are actually the same things, and I'm going to explain what that means. So if you overlay a triangle onto a grid, you'll actually be able to manipulate it in a way that you probably wouldn't be able to without the grid, or at least it wouldn't make as much sense. So now my b side has actually become my x, if you notice that. This is straight along the x-axis, whereas my a side is actually my y-axis. And thinking of it like this, because if I draw a line straight over whatever the length of a, that's the y value. So this upper corner here would be a point in space. You consider it 3, 4, right? The x value would be 3, the y value would be 4, and this would be the length or the distance that you travel from the origin to that point. Since the point is 3, 4, this x value would be 3 and the y value would be 4. So I have two sides that are 3 and 4. To get the final side, you square the 2. 3 times 3 is 9, plus 4 times 4 is 16. That's 25. The square root of that is 5. This is a 3, 4, 5 triangle, right? And we've just used the Pythagorean theorem to get there. Well, it's neat by swapping the sides but with x's and y's, and this final hypotenuse to be the magnitude or the distance. We've gotten x squared plus y squared equals the magnitude squared, right? So it's the same exact form that we've kind of manipulated a little bit to our will. This has another use, whereas if we overlay a unit circle around it, we actually can think of it in terms of sine and cosine. The reason for that is along this circle, what we're going to do is place the points directly on this. And with unit circles, the interesting quality is the radius of that circle, or the c value, or the hypotenuse, or the magnitude, or whatever you want to call it, is always 1. That's why it's called a unit circle. And what that gives you is the ability to now call the x-axis cosine instead of x, and sine instead of y. And at every point along these, it will equate to a sine wave or a cosine wave attributable to that angle, and the angle being right here. We're not talking about the angle just yet, but here what we've done is take sine squared plus cosine squared equals magnitude squared. And because the magnitude is always 1, you now have our original identity. What this means a little bit further is the reason that the radius on this circle is always 1 is because a sine wave has a maximum value of 1 and a minimum value of -1. Same with a cosine wave. What I've done here is the x value is actually 0 to 2 pi, but I've replaced it with essentially integer values, so 0 to 6.2 something. And same here, and then we have the y range. And I've done my best, I didn't do a perfect job, but I've done my best to attribute the locations on these graphs to associate with one another. And again, it's not a perfect job, but this would essentially be pi halves, more or less. And at pi halves, on a unit circle, the sine value is 1 and the cosine value is 0. So if we go there, it's 1, and here the value would be 0. So it's hopefully accurate enough to get the idea across. If we actually go to plot those, it looks like this. So here we have our angle, and what I did was segregate this by essentially 45 degrees. You go 0, 45, 90, 135, 180, and you continue around all the way to 360. In radians, it would be pi fourths, pi halves, 3 pi fourths, pi, and continue on. So that's what we have as far as the angles. And then we have the cosine value, the sine value, and at all points, the magnitude is going to be 1. So it's going to look something like this. And what I've done is draw essentially the magnitude to those points. And again, it doesn't line up perfectly, but I think you get the point. What you can view that as, though, is that each one of these points gives us a triangle. And the triangle goes up, and again, it's not a perfect overlay, forgive me, but the triangle goes up, and you get a y value, and you get an x value. And you have that angle. It's going to be pi fourths in this case. And the magnitude is going to be 1. So in this case, this is x, this is y, or also a and b, or b and a, whichever you want to call it. A squared plus b squared equals this radius, which is always 1. So these are all equal formulas. A squared plus b squared equals c squared. X squared plus y squared equals the magnitude squared. Sine squared plus cosine squared is the magnitude squared. And the magnitude is always 1. So sine squared plus cosine squared equals 1. This is where we started. And finally, what I mentioned at the start was when you start to manipulate this formula to your will, you may want to solve for different things. You may want to solve for cosine, you may want to solve for sine. Well, it just so happens you can treat this just like any algebraic formula, where I can pull sine to the opposite side just by subtracting it, and now you get sine squared equals 1 minus cosine squared. And cosine squared, I can move sine to the other side also by subtracting it. So you get cosine squared equals 1 minus sine squared. So these are actually the exact same identity, but what's frustrating is they'll actually treat them separately in many cases. But hopefully this gives you an understanding of why this is a thing, why this actually works. And hopefully you won't be left with just having to memorize this identity, which I don't think is a very useful way to do it. And once you have it, once you can figure it out, you can then manipulate it and solve for different things that work for you.